In this session, we're going to see about graphing polynomial functions, and we're going to do it the easy way. You're going to like this, watch. We're going to look at behavior at the ends, behavior at zeros, and the y-intercept. See? Easy. When we talk about behavior at the ends, we're looking at if the ends point in the same direction or if the ends point in opposite directions. And what's going to determine this is the degree of the polynomial. It will be the case that if the degree is even, then the end behavior will match. If the degree is odd, then the endpoint behavior will not match. Now, remembering that real zeros of polynomials are associated with X intercepts, what will determine what happens at an X intercept or a zero is indicated by the multiplicity of the zero. You may remember that at a zero of even multiplicity, the graph will touch the x-axis, and at a zero of odd multiplicity, the graph will cross the x-axis at that intercept. And finally, we're going to consider the y-intercept, and as you know, for any y-intercept, x is 0, and if we have a function f of x, then what we're looking for is the point 0, f of 0. In other words, we put 0 into the expression for the function to find out where the graph crosses the y-axis. We're first going to examine behavior at the ends. I have here graphs of 3 polynomial functions. One of them is y equals x cubed. One of them is y equals 5x cubed plus 10x squared minus 5. The other one's y equals x to the 5th. We'll deal with that in a couple of minutes here. What I want to point out is that for the graph of y equals x cubed, the ends point in opposite directions. Right? This is one of our basic functions. You know that it goes up into the first quadrant and down into the third quadrant. What's important to note is that the exponent is 3, x cubed, and this would be an odd degree polynomial. And what I have here in y equals 5x cubed plus 10x squared minus 5, the biggest exponent is 3, and so this is also an odd degree polynomial. You can think of odd as not matching, and we have a graph that again points up in the first quadrant and down in the third quadrant, but it's got a little wiggle in the middle. And this wiggle is due to the zeros and what happens near them. But overall, what we're looking at is that an odd function has endpoint behavior that doesn't match. For our third graph here, we're looking at y equals x to the 5th, which also points up in the first quadrant, down in the third quadrant. We may be tempted to think that this is basically just that cubing function, but if you look closely near the origin, what you'll see is that y equals x to the 5th actually flattens out more and has more severe bending in the arms that go up and down than y equals x cubed. I wouldn't hold you responsible for that kind of detail in your drawing. What I'm really after is that the degree of y equals x to the 5th is odd. And so if you see an odd degree polynomial, you know that the endpoint behavior is going to be such that the ends don't match. They point in opposite directions. You may also recall that if a coefficient were negative, then the graph would be upside down, but that would not affect the endpoints not matching. By contrast, we can consider here 3 other functions: y equals x squared, y equals x to the 4th, and then y equals x to the 4th minus 3x cubed plus 2x. And what I see here is that each of these functions is an even degree polynomial. And I have y equals x squared here just for comparison. As we saw with the previous graphs, when the exponent is higher, as in y equals x to the 4th, the graph flattens out more at what would be its vertex at the origin than it does for y equals x squared. So they grow at different rates. They flatten out in different ways near the origin, but the ends point in the same direction. And of course, if a coefficient were negative, then the ends would point down, but they would still be pointing in the same direction. as each other, that is. And then finally here, this y equals x to the fourth minus 3x cubed plus 2x. The ends point in the same direction, and then we have this kind of wiggling in the middle there, and that would be due to the zeros of the polynomial. So if I can scroll back up here, then what we see is that if a polynomial is of odd degree, the ends will point in opposite directions. If the polynomial is of even degree, then the ends will point in the same direction. We're going to combine that with what we know about multiplicity to let us know what happens at x-intercepts, and what we know about finding y-intercepts to produce graphs of functions. For our first example, we're going to sketch the graph of p of x equals 1/4 times the quantity of x minus 1 cubed times the quantity of x plus 3. And we are going to do this the easy way, easy y. For ease, we're looking at the ends. Z, we're looking at behavior at zeros, which in this context is closely associated with x-intercepts. And then finally for y, we're looking at the y-intercept. As far as the ends, we're looking at the degree of the polynomial. And if we were to multiply out x minus 1 cubed and then multiply that by x plus 3, I'm sure you can confirm this is a fourth degree polynomial. Being that it is a polynomial of even degree, the ends will point in the same direction. Because the coefficient out front 1/4 is positive, that direction is up and not down. As far as zeros are concerned, or the behavior at the zeros, because our factors are x minus 1 cubed and x plus 3, our zeros are 1 and -3, and as you may recall, real zeros lead to x-intercepts, so we have x-intercepts at 1, 0 and -3, 0. It's part of what we were asked for, so I'm going to go ahead and highlight that. But now we're looking at the exponent. Not to be confused with the degree, we're now talking about multiplicity. X minus 1 is a factor of multiplicity 3, or it appears 3 times, so x equals 1 is a 0 of multiplicity 3. The 0 of odd multiplicity indicates a place in the graph where we cross the x-axis. And then while we don't formally talk about the multiplicity of 1, it is odd, and so we should cross the x-axis at that location. And then finally the y-intercept. The y-intercept is going to be where x is equal to 0, and so computing p of 0, I'm sure you can confirm we're going to get -3/4. So the actual y-intercept is 0, -3/4. We were asked for that as well. Oh, let me put a parenthesis there. And so I'm highlighting that, circling it. I'm going to plot points at our intercepts. So I've done so at -3, 0, at 0, -3/4, and at 1, 0. And our endpoint behavior, I'm going to put little notes to myself. We're going to point up in the second quadrant and up in the first quadrant. And what we need to do is connect those arrows and those dots in such a way that we're respecting all of the information that we have. In other words, our graph is going to point up in the first quadrant, pass through the point 1, 0, and I seem to remember something about graphs tending to wiggle if the multiplicity is, say, 3. We're going to cross 0, -3/4. Missed it a little bit, but I'm really close. And then on up through -3, 0. These, we should have arrows pointing up. As you recall, you just saw the graphs of some polynomial functions, and they tend to go nearly vertical at the ends. They don't go off and do, kind of horizontally oriented stuff. So don't do that, please. They point up, up. And let me erase my blue arrows so it doesn't look like we have something that's not a function. And there we go. Now, if we compare this graph with the actual computer-generated graph, which I have down here, we'll see that we were close. We were a little off. How far off? I don't know. Let's see. I'm going to lay this on top of the other graph here and get my axes kind of straightened up here and there. The wiggle wasn't perfect. The local minimum wasn't perfect. I do believe, though, as far as I'm concerned, we got the major points. That is, up as far as endpoint behavior, pointing up on both sides. We got the X intercepts, and we got the Y-intercept. We even got a nice little wiggle there. That was cool. As far as the local minimum, I see the one I drew goes down to about -3 at that local minimum. The real one goes down to about -6. I don't need you to know that. In fact, if you ask me how far down is this supposed to go at the local minimum, I'm going to say all the way down to calculus, because that's what you need to have in order to figure out exactly where that value is. So we aren't going to bother with that kind of detail. We're going to be content with endpoint behavior, behavior at zeros, the y-intercept. We're graphing the easy way. Next, we have a polynomial, the expression of which is not even factored. We're going to sketch the graph of p of x is equal to x cubed plus 3x squared minus 4x minus 12. Be sure to label intercepts. Intercepts, those are like zeros. In fact, what we're going to do is we're going to factor the expression to figure out what the zeros are. That'll tell us the x-intercepts. But remember, we're going to graph the easy way. And so first, I want to know what's going on at the ends. I can see that we have a third-degree polynomial because the biggest degree of terms is 3. And so as far as the endpoint behavior, we're going to be pointing in opposite directions. And because the leading coefficient is 1, it is not an upside-down graph situation. Our graph is going to point up in the first quadrant and then down in the third quadrant. If we had a negative coefficient, we'd be pointing up in the second and down in the fourth. For our zeros, what we're going to do is find the zeros of the polynomial, which means we're going to set x cubed plus 3x squared minus 4x minus 12 equal to 0 and solve that equation. This thing has 4 terms. We're actually going to be able to factor the expression by grouping. We can factor an x squared out of the first pair and -4 out of the second pair. We end up with x squared times the quantity of x plus 3 minus 4 times the quantity of x plus 3. And if you remember how to factor by grouping, then you know we can factor out an x plus 3. We're left with x squared minus 4. That product equals 0, and so x plus 3 times x plus 2 times x minus 2 equals 0 is the equation we're ultimately solving. And so our zeros are going to be x equals -3, x equals -2, and x equals 2. Rather than saying those are equal to 0, since I'm not really asked to find the zeros, what I'm really doing is finding the x-intercepts, which are a result of having zeros that are real. We can say then that the x-intercepts are from the zeros -3, 0, -2, 0, and 2, 0. I'm going to go ahead and plot those, -3, 0, -2, 0, and 2, 0. I should probably label those numbers. And then for the y-intercept, we're looking at p of 0. Let me get some room here. And p of 0, I'm sure you can figure out, is -12. Therefore, the y-intercept, and I'm putting it up here just so it's all nice and tidy, is 0, -12. So I was asked to label that, and there it is. And I'm just going to kind of do my best here. It's down here on the y-axis at -12. Now, I have identified my endpoint behavior and my zeros. And because the exponent of each of the factors was 1, multiplicity being 1 means there's not really anything interesting going on at those x-intercepts. It's just going to cross normally. No wiggling, no bouncing. It comes from up in the first quadrant, goes down through the point 2, 0, hits the -12 on the y-axis, comes back up to hit -2, 0, and then we're going to bend back down through 0, -3. Don't like how that went at the end there. Shouldn't really be a wiggle, just because I'm not perfect. There we go. And an arrow pointing up, an arrow pointing down. Let me erase my little indicators that I had, and now we have the graph of a function. One thing that students sometimes do is they find themselves in a pickle and they end up crossing the axis where they're not supposed to. Don't invent X-intercepts. You found all the X-intercepts when you found the zeros. They come from the factors, nowhere else. Now, if we compare this with the computer-generated graph, then we'll see that we got some of this right and a little bit off. Let me go ahead and superimpose this on here again. Okay, pretty good, I suppose. Oh my gosh, look at that. My local minimum is on the wrong side of the y-axis. We got the major points. That is, up in the first quadrant, down in the third quadrant. We got our x-intercepts. We got our y-intercept. As far as the detail as to where the local minimum occurs and how far down it goes, that goes all the way down to calculus. And so if you draw something that is reasonably accurate, I will be pleased. Same thing as far as the local maximum up here in the third quadrant. I'm not going to hold you responsible for that level of detail. If you get something that hits all the major points, that is, the endpoint behavior is correct, your intercepts are correct, and you've drawn something that reasonably connects all that information, I will be happy. For our last example, we're going to sketch the graph of f of x is equal to -1/9 times the quantity of 2x minus 1 squared times x plus 3, the quantity cubed. First thing I notice, the coefficient in the front is -1/9, and so whatever I'm expecting, it's going to be upside down. Now, we're going to graph the easy way, which means we're looking at behavior at the ends, behavior due to zeros at the x-intercepts, and the y-intercept. If we were to multiply this polynomial out, which you can do to verify if you would like, 2x minus 1 the quantity squared would give me a term that involves x squared. X plus 3 the quantity cubed would give me a term that includes x cubed. Taking those two and multiplying them together, we would find out that this is a fifth degree polynomial. Being a fifth degree polynomial, the endpoint behavior is opposite. They don't match, but due to the negative coefficient out front, that endpoint behavior is going to point up in the second quadrant and down in the fourth quadrant, which I'm going to go ahead and mark on my graph right now. The zeros give us x-intercepts when they are real. Because of the factors, the zeros are 1/2 and -3. And so the x-intercepts are 1/2 0 and -3 0. 2x minus 1 is squared. Therefore, it's a 0 of even multiplicity, which means we are going to touch the x-axis at that 0, that x-intercept. That x plus 3 quantity cubed gives a 0 of odd multiplicity. Therefore, at the x-intercept, we will cross the x-axis. And since I was asked to label the x-intercepts, I'm going to go ahead and circle all of that, saying those are my x-intercepts. For the y-intercept, we're looking at f of 0, which I'm sure you can confirm is going to be -3. Therefore, our y-intercept is the point 0, -3. Let me go ahead and circle that. And now I'm going to plot these points. 0, -3, -3, 0, and 1/2, 0. Now, I'm supposed to come from the bottom right down there in the fourth quadrant, and at -1/2, I'm supposed to bounce off the x-axis. Then I'm supposed to somehow cross through the point on the y-axis at 0, -3, and then end up bouncing back and probably wiggling here at x equals -3. I'm going to clean this up and then see if we can draw what we're supposed to. So from down in the fourth quadrant, bounce off the x-axis at x equals 1/2, cross the y-axis at y equals -3, and then I'm going to give a little wiggle right here where it crosses -3, 0 because of that multiplicity 3. I'm going to label -3, 1/2, and -3 on the x and y axes respectively. And if we want to compare this with the computer-generated graph, then we will see that we got the major features, that is, pointing up in the third quadrant, down in the second quadrant. You know, let me clean up those little arrows that I had drawn as indicators to myself. And I noticed that the computer-generated graph goes much more vertical than the one that I drew. You know, that's actually okay with me. What wouldn't be okay is if it starts veering off to the side. Polynomial functions just don't do that at their endpoints, so don't do that. And again, what I can see is my local minimum was at about -4. The actual local minimum was at about -8. Again, calculus would be required to get that detail just right. What I did get just right were the x and the y-intercepts. Again, if you can connect all this information in a nice, reasonably shaped way, I'll be happy.